I'm supposed to talk about the next universe. I think that's slightly misleading. I should warn you several things I'm not talking about, and if that's what you came to hear, you're welcome to leave. I'm not going to say anything about heaven, and I'm not going to say anything about hell, or utopia, or chaos, or dystopia, or what. I'm not even going to talk about parallel universes, because people think of our universe and another one sort of sitting next to us, and that sort of thing. In fact, I'm a little worried about the word universe here. Because to me, the universe encompasses all things that we have access to, or in principle access to. And I am going to say that something happens. In fact, I've given a title to this kind of talk, which is before the beginning and beyond eternity. So this gives you some idea. The usual picture of cosmology is that there was a beginning, which was the Big Bang, and the universe expanded, slowed down a bit, and now it's expanding in an accelerated way, and this expansion will continue indefinitely. And so that is the universe according to conventional cosmology, with a little tweak at the beginning called inflation. Now, when I say the universe, I mean more than that. So when we talk about the next, I say there is something else happening after what you might call eternity, and there was something before the Big Bang. However, information can get across from one to the next, so it's not as though they're separate universes. They're all part of one universe, and I want to say something about, in fact, observations, which in my view give a good indication that there was something going on prior to the Big Bang. But of course it's calling about the next, so let me first start talking about the future. So the picture we have of the universe's future is that it's dominated by, well, what people call dark energy. I think that's a very misleading term, because it's not dark and it's not energy in any normal sense of the word. It's certainly not dark. There is material called dust, which is dark. That's sort of, you see dust around a galaxy, it's clear that's dark. Whereas this stuff isn't dark, you just don't see it at all. It's transparent. It's not really energy, because it has a curious feature that energy normally has. According to Einstein, E equals mc squared, energy and mass are equivalent, and mass is attractive gravitationally, so it should pull things together, whereas this so-called dark energy pushes the universe apart. However, in 1917, Einstein introduced a term into his equations called the cosmological constant, which was a thing called lambda, and although he did it for the wrong reason, because he wanted a universe that was static, never changing, and he needed this term to make it static and never changing. But then when he realized that the universe wasn't static and never changing, it was actually expanding, he regarded the introduction of this term as a mistake. He called it his greatest mistake. The thing about it is, though, it happens to be even Einstein's mistakes turned out to be right. And in this particular case, it does seem to be that the lambda that he introduced is what's doing this accelerated expansion, which is now observed. Sometimes people refer to it as quintessence, sometimes they call it dark energy. And to me, it's just this term that Einstein introduced for the wrong reason, admittedly, but it does all you want. And what's more, even though people were very surprised when they saw that the universe was doing this exponential expansion, looking at very distant supernova stars, exploding stars that outshine the entire galaxy within which they reside, and you can spot them way, way off in great distances. And so the conclusion was made from this in around about 1998 that the universe was accelerating in its expansion, and people are often express a lot of puzzle about this and introduce this term dark energy. However, if you go back to the old cosmology books, starting, I don't know when the first one was, but ever since 1917, and certainly all the ones I knew, this term, the cosmological term, was in that, and it gave you the prediction that the universe would do this. Of course, we didn't know it was there, and that was perhaps a bit surprised to find that this term was actually playing a role. To me, it's absolutely vitally important. It took me a long time, I should say, but for my own wrong reasons, I didn't believe in it for a while. But then the observational people told me, no, you've got to take it seriously. So I started taking it seriously, slightly against my own views initially, and then realizing that did something for me which was very important. So let me tell you about that a bit. Well, let's think about the remote future of our universe. Well, it's doing this accelerated expansion. We have these galaxies like ours, and they will, in clusters, these clusters will tend to be more or less bound, but they also have superclusters, which are clusters of clusters, and they will tend to disperse in a general way. Things will get further and further apart. They'll take part of this in this exponential expansion, and things will get more and more rarefied as time goes on. And in a certain way, they get more and more boring. Let me explain a bit more about that. You see, the universe, an essential feature in what I want to talk about is one of the most important laws of physics. And it's a nice law because people can talk about it without really knowing what they're talking about. It's the second law of thermodynamics. Now, the second law of thermodynamics, in rough terms, tells you that things get more and more random as time goes on. Okay, well, that's reasonable. You know, if I take this glass of water and I put a drop of ink in it, I don't think I will, but it spreads itself all over the water, and this gets more and more random. And there's a thing called entropy, which is a measure of the randomness, and this entropy is increasing. That's the second law of thermodynamics. It tells the randomness increasing, which is quite a, not a very nice law, you might say, but on the whole, it's quite something you might believe in. And well, what is the biggest source of entropy in our universe? Well, people used to think it was this cosmic microwave background. I'll say something a bit more about that. This is radiation coming in from all directions, which was discovered almost exactly 50 years ago. This is electromagnetic radiation, essentially microwaves coming in from all directions, pretty well uniformly all the way around the sky. And this was sometimes referred to as the flash of the Big Bang, cooled down by the expansion of the universe. And that's called the microwave background. And this microwave background was, when it was first found, thought to contain a huge amount of entropy. And so people used to say, oh gosh, most of the entropy in the universe is in this microwave background. But then people started to worry more about these things called black holes, which collapse stars, or in our Milky Way galaxy, there is an absolutely huge black hole, which has a mass. Black holes have masses. This mass is about 4 million times the mass of the sun. So it's pretty enormous. And it sucks other things in. Gas and stars now and again will fall into it. And once they fall in, they can't escape. And that's one of the implications of Einstein's general relativity. So we come to believe in this. It took, I may say, cosmologists quite a long time to take them seriously, but they did eventually. And now they're seeing them all over the place. The Andromeda galaxy has a black hole which is a good deal, I forget whether it's 40 times, something like that, as big as ours. And that will play a role in what I want to say shortly. But those objects, the black holes, are where most of the entropy is. So we have entropy finding its way into these black holes. Okay, now the universe expands, some things fall into black holes, sometimes the black holes, things will escape from the black holes, but on the whole the black holes will dominate what used to be the galaxies. And then what will happen? Well, as the universe cools down, the black holes start to radiate away. You see, there's a thing called Hawking radiation. Stephen Hawking showed that black holes, well, he calls them black holes are hot. I think that's a bit of an exaggeration because they're not that hot. In fact, it's worth thinking about how hot they are. The hottest ones are the smallest ones. And the smallest ones we have any good astrophysical reason to believe in are maybe about 10 times the mass of the sun. Those are the hottest ones. How hot are they? Well, if you think of the coldest temperature that's ever been artificially made on the Earth, and that's pretty cold, you're in the right ballpark. It's around about that. So not very hot. The big ones are much, much colder. The supermassive one in our galactic center would be enormously colder than that. Essentially absolute zero. But as the universe expands and expands and expands with exponential expansion, it will cool down. The microwave background cools down, and then the black holes will be the hottest things around. And when they're the hottest things around, pretty cold, but hottest things around, they will radiate away, And as they lose energy in radiation, E equals mc squared, they lose mass in radiation, therefore they get smaller and smaller and smaller and smaller until finally they disappear with a pop. Now I'm using the term pop rather than bang because on cosmological scale it's nothing. Okay, it wouldn't be nice for it to go off in this room, I grant you, but nevertheless it would be pretty small on astrophysical terms. So that's what happens to these black holes. How long will it take for them all to disappear? Well, you've got to think about the biggest ones, which will be the coldest ones, and therefore they will the last ones to begin to get cold, and how it take the longest to get cold, to disappear, I mean. The biggest ones will take a long time. They will take around about, to get the rough idea, 10 to the 100 years. So it's a sort of googol years. If you know what a googol is, write 1 0 0 0 0 with all 100 zeros. And that will be roughly within, I don't know how many orders of magnitude, but you get a rough figure. For that kind of figure, you have to wait that long before these black holes go off pop. Now, I can't think of anything much more boring than sitting around waiting for a supermassive black hole to go pop, I have to say. But if you think that's boring, the really boring time is after they've all gone. Now, that's really boring. And I was worrying about, you shouldn't use emotional arguments in science, I suppose, I don't know. But anyway, I was sitting in my office at home and thinking, this is a pretty boring thing to happen to this wonderful universe of ours. And it didn't seem to me that was, what's it all for, sort of thing. I don't know what that kind of argument really means, but it did seem to me rather a sorry fate for this wonderful universe. And then I started to think, who's going to be bored by this universe? Well, not us, but at least we won't be around. Who's going to be around? Well, mainly photons. They were mainly, particles of light, mainly photons. And it's very, very hard to bore a photon, I'll tell you. It's hard to bore a photon for two reasons. One is they probably don't bore easily because they don't have experiences. Okay, I'm not really talking about that, though. The reason it's hard to bore photons is they don't actually experience the passage of time. This is a feature of Einstein's special theory of relativity, that the faster you move, the slower the time takes to pass by. And if you happen to be a photon, eternity is as nothing. So I thought to myself, gosh, these photons will hit eternity and go right through it. Now, when I say that, you see, you have to... I've been working on these things for a long time earlier, how to treat infinity. Now, there's a very nice way of treating infinity. Those of you who've seen the Escher pictures called circle limits, there's a nice circle, and then maybe they're angels and devils, black and white things, and they all go right up to the edge. And you have to imagine the angels and devils look as though they get smaller up to the edge, but they think they're the same size as the ones in the middle. The kind of geometry that's being represented here it's a conformal representation. That means that small shapes are accurately represented, even there's no distortion. So the eyes of the devils, for instance, would be the same shape right up near the edge, even though they look much smaller. The devils think they're the same size as the ones in the middle, according to their own geometry. But this picture, the point I want to get to here, is that this boundary, the circle around the edge, represents infinity. And if you take a kind of geometry which doesn't worry about lengths and things like that, just worries about angles or shapes, then infinity can be represented in a nice way, and you could imagine something on the other side of that infinity. So the picture I had, and this is the kind of mathematical trick that we've been playing with for many decades actually, is to treat infinity as a nice boundary. And you can do that nicely for photons. Now, this is where the physics starts to get a little involved. But not only do photons not experience the passage of time, but the scale, the famous equations of Maxwell, which tell you how light behaves, and the light staring at me, for instance, these are photons, in a classical way of thinking about them, but they're also waves of electromagnetism. Radio waves are also interplay between electric and magnetic fields that shoot each other across the universe. And those equations which govern the electric and magnetic fields, the Maxwell equations, are completely insensitive to change in scale. It's rather a remarkable thing. You can squash down here and stretch out here as long as the squash and stretch is uniform. So if you stretch as much in this direction as that one and that one, that's called a conformal stretch. That stretch is insensitive. And Maxwell's equations are insensitive to that. So that as far as Maxwell's equations are concerned, they don't know infinities. They don't even care. They could go shooting right through infinity to the other side if there was another side. So I was used to thinking of things like this, just sort of mathematically and not taking it too seriously. But somehow, as far as the photons or electromagnetism are concerned, infinity is just like anywhere else. So eternity is just the same old place as anywhere else. It's only things which with mass that notice the difference. You see, we have wonderful clocks. I don't know what kind of a clock this one is here, but we do have wonderful clocks. It's the wrong way around, that's what I see. We have wonderful clocks in physics, nuclear clocks, atomic clocks, nuclear clocks. And these are very, very precise, extraordinarily precise. And in fact, if you want to know about distances, see, there used to be, and probably still is, the meter rule in Paris, which is used to be the definition of the meter. But now that's lousy. It's not nearly good enough. But times can be measured extraordinarily precisely. So the meter is now a very precise fraction of a light second. So it's the length it takes, certain fraction, very definite fraction, which I've forgotten, but never mind, that it takes light to travel. And that fraction of a second is a meter. So if you don't know distances, if you can squash distances in and out, that's the same as squashing times in and out. So that relates to these photons not caring about infinity. Infinity is just like a finite boundary to photons. In fact, anything without mass doesn't care about the scale. And that's not only true of Maxwell's equations, it's true of the equations of the strong and weak interactions, things called Yang-Mills equations. Don't worry about them, I'm not going to write them down or anything. These equations are insensitive to the scale. It's only the mass which knows the scale. And the mass knows the scale in a very fundamental way according to, well, it's really the two basic, most fundamental physical laws of the 20th century. One, of course, is Einstein's E equals mc squared. In other words, apart from the speed of light, which is a constant, E and m, in other words, energy and mass, are equivalent. The other is E equals h nu, or hf, or whatever you like to call it. E is energy again, and the nu, or the f, is frequency. So Planck's, there's an h there too, which is again a constant, that's Planck's constant. But that equation is telling you that energy and frequency are equivalent. So you put the two together, they tell you that mass and frequency are equivalent. So this means if you have a massive particle, it is a little clock. And it's a linear clock with a very, very well-defined, absolutely extremely precisely defined frequency. And atomic and nuclear clocks are based on the fact that mass and clock rates are basically equivalent. But you have to have mass to be able to measure the rate of passage of time. If you don't have mass, large and small, long time and short time are equivalent. Okay, so here's the question. If you're allowed to squash down infinity and there's only photons running around, what about where are they going on the other side? Okay, well, the story that I'm trying to promote here, this is a book which I wrote and it was published in 2010. It's called Cycles of Time. A lot has happened since the publication of that book, but the ideas are basically what I say there. We have to go back to the Big Bang now and ask the same sort of questions. Not how boring it is, well, it's the same sort of thing, but it's boring for a completely different reason. In fact, really what I want to say is that mass becomes irrelevant when you get right back down into the Big Bang. Let's go back in time, and you find that it gets hotter and hotter and hotter and hotter. It gets so hot that the energy in the mass of particles becomes utterly irrelevant. And it's the energy of their motion which is really relevant. And so you can forget about the mass. The closer you get back down into the Big Bang, the more irrelevant mass becomes. And therefore the same ideas apply for a sort of opposite reason. Same ideas apply that mass becomes unimportant and particles are massless like photons. Everything's like photons. And so they don't care about scales of distance or time. And then, now here's the outrageous thing. What I've said so far is accepted pretty well. The outrageous thing see, I used to call this idea an outrageous idea so as to get in there first, because everybody's going to say, they read this, they'll say, well, look, that's an outrageous idea. I say, yeah, I said so already. But I'm not sure it was such a good idea now, but I'm trying to get people to take me more seriously now. But the point is, the outrageous idea is that what you find after the infinity of the remote future is the Big Bang of another eon. So the next universe, if you like, although I'm not calling it actually another universe, but the next eon, I use the word eon, which is from our Big Bang to our absolutely remote future is our eon. There will be another eon, A-E-O-N, beyond that, and there was one before. Now, I took care to look up in the dictionary to see how long an eon was, and I was happy to find that it wasn't an indefinite length of time. It's a long time, but there's no number of years or anything which seems to be an eon, so I thought, fine, because my eon is actually an infinite number of years. If you measure it in terms of years, but you see, if you're in the remote future when there's nothing with mass around, then you don't care about years. You see, the photons don't care about years. There are little glitches little points I should make if I was going to make this story complete. I don't know how much time I have here. A little bit more. Okay. Now, so we have our Big Bang. You could stretch, you see, you use the same kind of mathematical trick. You stretch it out by this conformal trick. You expand time and space both out, and you get a nice smooth initial boundary, which can be joined on to the nice smooth final boundary of the eon prior to ours. And then our final boundary, our infinity, glues on nicely to the Big Bang of the next eon. And the whole thing will only work if the physics at the time of crossover from one to the next is essentially with no mass left. So you have to make sure you get rid of all the mass before the crossover, and the mass comes back gradually afterwards. Well, according to particle physics, and you've probably heard about the Higgs particle and all this, according to standard physics today, mass really does come in at a certain very early moment. And before that, everything is basically massless. What's less conventional is that the mass of whatever particles are left, okay, I talked about photons in the remote future, but there will be electrons running around, some rogue electrons. Some will fall into black holes, but they won't all fall into black holes. There'll be some running around as well, and they behave as little clocks, so we've got to deal with them somehow. So what I'm saying is that over vast periods of time, probably much longer than it takes the big black holes to disappear, there will be a fade out of mass and a sort of an inverse Higgs process. That's not altogether conventional, I should say, but doesn't go against any of the conventional ideas in physics. It's just not usually suggested. And the whole scheme, you need to write down a lot of equations and all that. You'll be glad to hear I'm not going to do that. I'm not allowed to anyway. In this talk, I'm supposed to order it with mouth and hands, as far as I know. So I'm using hands. But anyway, so the idea and the equations work pretty well. Tell you how you get across from one eon to the next. Okay, you could say, okay, that's a nice idea, but then how are you ever going to know? How is anybody ever going to know if such a thing is possible? And as I said, I'm not really allowing myself to talk about one universe unless they can, in some sense, communicate. So I did think about this for a while. I thought, what kind of signal could possibly get through? What kind of signal could be so strong that it could get through from the eon prior to ours into our eon? So I tried to think of the most violent thing I could think of. Well, I have told you about the black hole in our galactic center, and I've told you about the black hole, which is a lot bigger than ours, in the Andromeda Galaxy Center. What I haven't told you yet is that we are on a collision course with the Andromeda Galaxy. So in a few thousand million years, give or take some, our galaxy is going to crash into the Andromeda Galaxy. It should be rather fun watching this happening. I mean, it'll take a little while before anything dramatic happens. But anyway, the point I'm really concerned with here is not that the stars will mostly miss each other, so it won't be as dramatic as you might wonder. However, the black holes in our respective galaxy centers they won't head-on collide, but they will very likely feel each other and quite possibly get attracted and fall into orbit around each other. If they don't, the first time, what will happen is the galaxies go through each other, slow down because of friction of dust and stuff, and then it'll come back again. And this may happen a few times, and there's no hope for those black holes to keep missing each other. They will eventually feel each other out and spiral around. As they spiral around, they will lose energy through gravitational ripples. These are waves in space-time that will be quite important in this process. And they will gradually spiral into the middle and swallow each other up with one stupendous explosion. I think one almighty boom. Now, boom isn't a very good description of it, because it will not even be something you could hear. It would be in the form of ripples in space-time, which carry away a significant fraction, a few percent of the energy in these black holes. Now, since these are already so energetic, that energy would be absolutely enormous. And there will be this signal going right out from the collision. That signal will go out to infinity. You might think it's all gone by then. No. This will make a mark on this crossover surface, and that mark could, in principle, be seen by us on the other side. Well, when I say us, our one will be the next people who are sitting up there listening to me, or some version of me, or somebody up there with 3 eyes and 4 heads, or whatever it is. And whatever the people in the next eon will be like, will no doubt, some of them will see the signal from the collision that our supermassive black hole and the Andromeda one create when they crash into each other. Now, what kind of a signal am I talking about that we might see? Well, we're talking about similar events in the eon prior to ours. So in some galactic cluster, there will be galaxies coming together, there are black holes colliding, and boom, there will be the explosions. These explosions will come out, will hit the surface of crossover between that eon and our eon, and they will hit the initial material. You have to go to the equation to see exactly what to expect here. But they will hit the initial material, which, in the way the equations work, I talked about dark energy, and it's the fact I don't like the word. I also don't like the term dark matter, which is something quite different. But we have these two terms used to describe, cosmologists say, the most mysterious things in the universe that we don't know what they are. But I think dark energy is Einstein's cosmological constant. Whether that means we know what it is or not is another question. But dark matter seems to be more like a real substance, which contributes to the mass of galaxies in a very significant way, and is the major part of the ordinary matter in the universe. Now, according to the scheme I'm describing here, each time you have a crossover from one eon to the next, it will produce a whole lot of new dark matter. And that dark matter will pick up the signals, which I'm talking about, the collisions between black holes, the signals that they shoot out, will hit the dark matter, and they will hit other material and cause it to produce a signal that we should be able to see. Now, what would these signals look like? They would look like rings in the sky, these circular rings, which would be rings of slightly enhanced temperature or slightly reduced temperature. And also the temperature will be more uniform around the ring than in most places. It will be slightly enhanced if the signal is coming towards us, and that's for the more distant sources, according to the theory. Slightly cooler if they're for nearer sources, because then it's going away from us, and slightly cooler. So this is the proposal, and I said things like this in my book, Cycles of Time, and I wasn't expecting, well, I tried to get people to look for these things, and some people in Princeton tried, but the way they tried didn't turn out to be a very fruitful way of doing it, as it actually turned out. I have an Armenian friend who tried, and he tried various ways, which a lot of people didn't think much of for a while, but he developed his techniques to be more in accordance with what people think. And in my view, he has some very significant signals. The signals in his case were that you took advantage of the fact that if a collision between black holes takes place, it's likely to happen again. You see, they swallow each other up, or maybe the big one essentially swallows the small one. So in our case, it will be the Andromeda black hole, which swallows our black hole, essentially. And then there will be others that come along, and they get swallowed. In fact, there are only, I can't remember, about 4 galaxies in our cluster, but you have bigger clusters somewhere, and there will be several times when these black holes will swallow others. And so you'll see, boom, one ring, another ring inside it, another ring inside that. And these rings will basically have the same centers. There will be concentric rings. And you look for concentric rings. Well, I may say we had a lot of trouble persuading people about this, partly because my colleague originally did his statistics in a rather unconventional way, which people didn't like. But the way he does it now seems to be the same as the way other people do it, and the signal does seem to be significant. We actually, the thing we did in a paper that we published about 2 years ago was to point out, a little bit unconventionally, not the normal way people do these things, but you see, people said, oh, well, you can see circles, you can see triangles, you can see squares, why, what's the point, you see? So what we thought, well, we look for circles. Then we have a device which means we can look by using the same algorithm for looking for ellipses, and more extended ellipses, more and more. And we found that if you distort the circles to an ellipse, where the ratio between the major and minor axis is only about, differs from 1 by only about 1 or 2%, the number of these things you see drops by about a factor of 3. If you look real ellipses which look like that, ratio 2 to 1, they've gone altogether. So there are circles out there in the actual sky, in this kind of way. If you look for ellipses, the more elliptical they are, they drop away and you don't see them. Independently of this, a Polish group looked a completely different way, much more directly what I'd said in my book, Cycles of Time. And this Polish group, quite independently, found, I should say, they're looking at the cosmic microwave background as we were, and initially in what was called the WMAP satellite. This was a satellite sent up, I don't know, a decade ago or more probably, looking at the cosmic microwave background and looking at variations in temperature over the sky. And they seemed to see also a signal which in their paper they claimed was there with what they said 99.7% confidence. So that seemed to be pretty persuasive. Nobody paid any attention to either of our papers for some reason. I was rather hoping, if they would at least complain about the papers, but it's been zero. I talked to this chap recently and said, well, how much response have you had? We've had absolutely nothing. 0. He said, yes, we had 0 too. Anyway, so recently both groups have been looking at the newer data, which is the Planck satellite data, which is a bit more precise and sophisticated, and we still find signals. I think we found our signals a bit stronger, I think. Their signals were, well, they didn't want me to say much about it, but it's just about the same as what they saw before. There are much more sophisticated ways of looking for these things, incorporating features that I didn't expect at all. You see, the thing I didn't expect was that when you look at the centers of these circles, they're all crowded in certain regions, but not all of them. But there are certain regions in the sky where you find vast numbers of them, and other regions far fewer. Now, this would seem to me that the eon before, this is our explanation, the eon prior to ours is very lumpy. That there are some absolutely huge collections, maybe lots of galaxies, maybe some particularly big ones with strong signals, where the black holes are enormous, and other places where they're not so big, or maybe not so many galaxies, or something, but very non-uniform. Now, although we didn't expect that, it's certainly easy to explain. And you can say, okay, there are these clumps there. And this is confirmed in both our cases and the Poles cases. Let's tell you about our cases. Because the way that we look for these rings was not by the temperature being warm or cool, it's just whether the temperature is uniform or non-uniform. And you find that in a certain region, where you see lots of them, they're all predominantly warm. In other regions, they're probably predominantly cool. Other regions, they're sort of in between. Now, how could that be if it was just random? But we can explain it, because we say the warm ones are very distant, very, very distant ones. The cool ones are relatively close, still pretty distant, but relatively close, and the intermediate ones are sort of just on the edge. And, okay, I don't know why it's like that, but it's certainly a good explanation. And you could actually take advantage of that. We haven't in our analysis, nor have the Polish people, but I think you could get a much more significant signal if you take that into consideration. But the real point I want to make here is that I don't see any way the conventional explanation can produce these kind of inhomogeneous patterns, because the conventional explanation is just random quantum fluctuations of a thing called the infoton field, which they claim is there.